This tutorial is discussing the mixtures of gases and partial pressures. When gases are mixed together, their molecules behave independently of each other. All the gases in the mixture have the same volume. All completely fill the container. Each gas's volume is equal to the volume of the container. So in other words, the molecules are being all spread out. Molecules are spreading out. And taking up the entire container. And the distance between them is so great that they don't really interact with each other. All gases in the mixture are at the same temperature, therefore they have the same average kinetic energy. For example, we have the composition of dry air. This is the air that we breathe on a daily basis. 78% of it is nitrogen, 21% of it is oxygen, and then we have smaller percentages of argon and carbon dioxide. However, they all interact independently of each other. They don't really acknowledge each other being there. In certain applications, the mixture can be thought of as one gas. Even though air is a mixture, we can measure the pressure, volume, and temperature of the air as if it were a pure substance. In other words, we can actually use the PV equals nRT equation while doing this. And pretend like all the gases are the same. So we can total up the gases. We can calculate the total moles of molecules in an air sample knowing the pressure, volume, and temperature, even though they are different molecules. And that's once again because they're not interacting with each other. The pressure of a single gas in a mixture of gases is called the partial pressure. We can calculate the partial pressure of a gas if we know that what fraction of the mixture composes of the total pressure. So in other words, how much of it is there out of the total. Or we know the number of moles of the gas in the container of a known volume and temperature. And we'll do examples of this later. The sum of the partial pressures of all the gases in the mixture equals the total pressure. This is called Dalton's law of partial pressure. Because the gases behave independently, we're able to do this. The partial pressure of each gas in a mixture can be calculated using the ideal gas law. So, as I said before, remember we can still use PV equals nRT. But here we have A and B mixed together. So we can say the pressure of A is the moles of A, RT over V. The pressure of B is the moles of B, RT over V. So we basically divided both sides by the volume to get the pressure by itself. The temperature and volume of everything in the mixture are the same. So this and this are the same because it's in the same container. The mixture are the same. The mixture is the total of moles of A and moles of B together. So this NA and NB added together. So from here we can say the total pressure is the pressure of A and the pressure of B added together. So let's practice this. In a partial pressure, find the partial pressure of neon in a mixture of neon and xenon with a total pressure of 3.9. So this is the total pressure. The volume is 8.7. The temperature is 598. And the moles of just the xenon is 0.17. Alright, so we don't know the total moles yet, but we do know the total of everything else. So why don't we figure out the total moles? 3.9 atm. We need PV equals nRT. The volume is 8.7. The N is our X right now because we need to figure out how much the total moles are so we can figure out how much of that is neon. R is 0.08206. That's atms, liters, moles, kelvins. And the temperature is 598. The first thing we'll want to do is multiply and divide. And then we find that X is equal to 0.69 moles. Now that's the total moles. We know that out of this, 0.17 is xenon. So I'm going to subtract 0.17 out of it to figure out just the moles of the neon. And that comes out to be 0.52 moles. Now, the actual question was asking about the partial pressure of the neon. So now that we have the moles of the neon, we can plug it back into this equation and replace the total pressure with an x because we're looking for partial pressure. So x is equal to 8.7. Now we're going to put 0.52 moles in for that x, where moles were before. 0.08206. And then 598. We're going to multiply and divide, and the pressure comes out to be 2.93 atm, which makes sense because it would be smaller than the 3.9. The fraction of the total pressure that a single gas contributes is equal to the fraction of the total number of moles that the single gas contributes. So in other words, the pressure of just the neon over the total pressure is going to be the same as the moles divided by the total moles. The ratio of the moles of a single component to the total number of moles in a mixture is called the mole fraction. This is the Greek symbol chi. That's what that letter is. It looks like a big X. So for gases, the volume percent over 100%. So chi, the mole fraction, is just the moles over the total moles. And that'll give you a decimal number. The partial pressure of a gas is equal to the mole fraction of the gas times the total pressure. So this is the moles over total moles. Or how we had it before is NA over N total times the total pressure. It turns out to be a ratio. So if we looked at this again, it's basically taking this times the total pressure. Alright, so let's do a couple examples of this. Find the mole fractions and partial pressures in a 12.5 liter tank. So that's our volume, total volume. 24.2 grams. Notice the symbol grams. We need to convert that to moles before we can go on. And 4.32 grams, got to convert that to moles, of 298 Kelvin. And that's going to be our total temperature. So let's convert the grams to moles first. So 24.2 grams of He over 1. We go grams to moles by looking on the periodic table, and we find that the molar mass of helium is 4.0. And that comes out to be 6.0 moles of just the helium. We're going to do the same thing with the oxygen, 4.32 grams of O2. We look on the periodic table, oxygen is 16.00. We're going to multiply that by 2, and it comes out to be 32.0 grams. And we divide it, and it comes out to be 0.135 moles of oxygen. Add those together, and it comes out to be 6.135 moles total. Okay, so we can figure out the total pressure here. The total pressure is going to be X. Remember, our equation is PV equals nRT. X times the volume, which is 12.5, is equal to our total volume now, 6.135 times our R, 0.08206, and our temperature in 298 Kelvin. I forgot my unit of moles over here. Okay, so our total pressure 12.5 liters times X is equal to 150.2.02. The moles canceled and the kelvins canceled. Divide by 12.5. Liters cancel. And X, our total pressure is now 12 atm. atm. Alright, so that's our total pressure. We want to know the partial pressure and the mole fractions. Well, the mole fractions, we're going to take the moles of 1 divided by the total moles. So HE is 6.0 divided by 6.135, and that equals 0.978. Total moles of oxygen is 0.135 over 6.135, and that equals 0.022. Okay, so there's our mole fractions of the helium and the oxygen. Here's our total pressure. We can multiply it to figure out our total pressure, or partial pressure. So our partial pressure of just the helium is equal to 12.0 times 0.978, which is then equal to 11.74 atm. We can either subtract it out to figure out the oxygen, or we can just go ahead and redo it with oxygen. 12.0 times 0.022 is equal to 0.264 atm. If you add these two numbers together, it should come out to be the total. So another way you could have done that is figure out the total the pressure of just the helium and then subtract it to find the oxygen. Let's do another one. Find the mole fraction of neon in a mixture with a total pressure of 3.9 atm. This is the exact same question we had before. Now we're just trying to figure out the molar pressure, the mole fractions. So let's go back to saying 3.9. This is exactly what we did earlier. 8.7 liters is equal to the X moles, 0.08206 and then 598. That comes out to be 0.69 moles like we had before. Now, to figure out the mole fractions, the moles of neon is going to be, we know that in the question is 0.17. The total is 0.69. That comes out to be 0.244. A couple different ways to solve it again. One way is to actually go through the, I'm sorry, this is xenon, I put neon. One way is to actually go through the steps again. So if we know that it's 0.17 and we have 0.69, so 0.69 minus 0.17, that comes out to be 0.52. So 0.52 divided by 0.69 is equal to 0.756. The other way is to know that these two things, when they're added together, all the mole fractions are going to equal 1. So you could have subtracted 1 minus 0.244 to get the rest of it. Gases are often collected by having them displaced water from the container. The problem is that since water evaporates, there is also water vapor in the collected gas, which means we have to account for that when we do the calculations. So what we're talking about is, you've seen this experiment probably in lab before, where you drop a metal into acid, and then hydrogen gas is given off from the metal, and it floats up. Well, and previously you probably just said, okay, it's creating bubbles and there's a chemical reaction. Well, now we're actually going to try to collect those bubbles. So it gets fed through a hose, and then this is completely filled with water originally. And then the gas goes up and pushes the water out. And that's how we collect the gas. The partial pressure of the water vapor is called the vapor pressure and depends only on the temperature. So you can use a table, which will be on the next slide, to find out the partial pressure of the water vapor and the gas you collect. If you collect a gas sample with a total pressure of 758 millimeters of mercury at 25 degrees Celsius, so you find 25 degrees Celsius, the partial pressure of the water vapor will be 23.78 millimeters of mercury. So the partial pressure of the dry gas, you would then subtract 758.2 minus 23.78 to get the 734.4. So let's do one example of these and then we'll be done with the partial pressures. 1.02 liters of O2 is collected over water at 293 Kelvin. Alright, so we need to go back to that chart and look at 293 Kelvin because it's collected over water. That's the key to look out over the chart. So that means we need to look at the chart. Alright, however, we notice that the chart is in degrees Celsius, not in Kelvin. It was 293 Kelvin, so we're going to subtract 273 to figure out the Celsius, and that comes out to be 20 degrees Celsius, which is right here, 17.55. The very first thing we want to do is subtract out that pressure because we want to find just the stuff with just the oxygen. So we want to get rid of the water in our scenario. So 755.2 millimeters of mercury minus 17.55 millimeters of mercury. That comes out to 737.65. Alright, so we're going to use our equation PV equals nRT, and we remember that our R is 0.08206 ATMs, moles, kelvins. The reason why I'm pointing this out is the fact that they gave us the pressure in millimeters of mercury. We need an ATM, so we need to convert it. So 737.65 millimeters of mercury over 1. Our conversion factor is 760. There's 760 millimeters of mercury, and that's just something you look up or you memorize, is in 1 ATM. Divide that out, 0.9706 ATM. Now we can take this pressure here and put it into PV equals nRT to figure out the number of moles. So the P is 0.9706 ATM. Our volume is 1.02 liters. That is equal to our N. We're looking for our moles. Our R is 0.08206 ATMs, liters, moles, kelvins, and our temperature is 293. Notice here we actually need it in kelvins, whereas the chart we needed it in Celsius. We multiply and divide, and we find that the moles are 0.04117 moles. for just the oxygen. However, they're asking for mass. And we know we can get from moles to grams by using the periodic table. 0.04117 moles over 1. 1 mole. And we're looking at oxygen. So oxygen is 16.0 times 2. 32.0 grams. That comes out to be 1.318 grams. And that explains how to calculate partial pressures and how they're used.